What we're going to do now is start to explore a series of tests to determine whether a series will converge or diverge. And the first one I'm going to go through right now is perhaps the most basic and we'll hopefully see the most intuitive. And this is the divergence test. And the divergence test won't tell us if a series will converge, but it can tell us if something will definitely diverge. So first let me write it in kind of mathy notation, and then we'll look at an actual concrete example of it. So the divergence test tells us that if the limit as n approaches infinity of a sub n does not equal 0, then the infinite series going from n equals 1 to infinity of a sub n will diverge. And we've already gone through what it means to diverge, that this sum is either going to go unbounded to positive infinity or unbounded to negative infinity, or it'll just oscillate between values. It'll never really approach a given sum or a given value. So that's what the divergence test tells us. And you're probably thinking, okay, all right, I can kind of get what this says, but where is this actually useful? And to see where it can be useful, let's look at a candidate series and see if we can figure out if it's going to diverge. So let's say I had the series, so the sum from n equals 1 to infinity. And in general, it doesn't always have to be n equals 1. It could be n equals 5. It could be n equals 0. The key is that this is an infinite series that we're talking about. So that's why we care about the limit as n approaches infinity. And so let's say we have the sum of 4n squared minus n to the third over 7 minus 3n to the third power. So given what we know about the divergence test, is this series going to converge or diverge? Well, let's just look at this. Let's look at what we're taking the sums of. So this is essentially, or this is our a sub n, if we're trying to match to the definition, or I guess the explanation of that divergence test. So let's think about what the limit as n approaches infinity of 4n squared minus n to the third over 7 minus 3n to the third is. And I encourage you to pause the video and think about that. Well, there's a couple of ways to think about it. One way is say, look, as n goes to infinity, the highest degree terms in the numerator and the denominator are the ones that matter. And so this is going to approach negative n to the third over negative 3n to the third, which would approach negative 1 over negative 3, which would be positive 1/3. Or we could say, if we want to do a little bit more, or do a little bit more systematically, limit as n approaches infinity, we can divide both the numerator and the denominator by n to the third. So if we divide the numerator by n to the third, this first is going to be 4 over n minus 1 over 7 over n to the third minus 3. And here it becomes clear. The limit as n approaches infinity, that's going to go to 0. That's going to go to 0. And so you're going to be left with negative 1 over negative 3, which is equal to 1/3. So notice, the limit of a sub n as n approaches infinity, in this case, is not equal to 0. Therefore, this infinite series will diverge. Now let's think for a second why this makes a ton of sense. Well, the only way that you're going to converge, that you're going to settle, remember, you're taking an infinite sum. You're taking an infinite sum of things. So the only reasonable way that something might be able to converge to a finite value is if every extra term you're adding is getting smaller and smaller and smaller, is approaching 0. If as n approaches infinity, you go unbounded, or if it's even equal to 1/3, this means that for very large n's, you just keep adding things that are getting closer and closer to 1/3. Well, if you add an infinite number of 1/3s together, you're going to go to infinity. You're going to be unbounded. You are going to diverge. So that's all that's telling us. Look, in order for something to converge, if you're taking an infinite sum of them, at some point these things are going to have to get really, really, really close to 0. If at some point they're not getting close to 0, there's no way it's going to converge. That thing will diverge. So hopefully that makes a little sense. And that also gives you, I guess, another insight on what the divergence test can't do. The divergence test can be used to show that something will diverge, but if something, I guess you could say, passes the divergence test, it doesn't, or I guess fails the divergence test, or if this isn't true, it doesn't mean that the thing is going to converge. And so let me give you an example of that. So this right over here, from n equals 1 to infinity of 1 over n, and this is actually the harmonic series right over here. This, if we try to apply the divergence test, we would say, okay, well, what's the limit as n approaches infinity of 1 over n? Well, hey, that is 0. As n approaches infinity, this is equal to 0. And so we could say, well, it's kind of failing the divergence test. So we're not, just by using the divergence test, we can't prove that this thing is going to diverge. But that doesn't mean that it doesn't diverge. It actually turns out, and we prove this in several videos, it actually turns out that this thing does diverge. This thing does diverge. It's just that the divergence test isn't enough. It's not enough of a tool to let us know for sure that this diverges. We'll see the comparison test and the integral test can either be used to prove that this, in fact, does diverge. And so you can definitely not say that if this does not apply for something, if you're taking the limit as n approaches infinity and it does go to 0, that thing still might diverge. It doesn't necessarily mean that it converges. Now, there are things that do converge where they do approach 0. So, for example, if I take the sum from n equals 1 to infinity of 1 over n squared, if I try to apply the divergence test, I have the limit as n approaches infinity of 1 over n squared. Well, this does equal 0. This gets really, really large. This thing is going to approach 0. And so, once again, this is, I guess, failing the test for divergence. Just with that alone, you don't know for sure that this thing is going to converge. It still might diverge. The divergence test just might not have been enough. Now, it does turn out, and once again, we prove this in future videos, that this thing does converge. This thing does converge, but not because it, I guess you could say, fails the divergence test. We have to use a different test to show that this does, in fact, converge, just as we have to use a different test to show that this does, in fact, diverge. Where the divergence test is useful is for the things that actually pass the divergence test. When you actually find that the limit as n approaches infinity of a sub n does not equal 0, like this case right over here. In this case, the divergence test helps us because helps us make the conclusion that this series definitely diverges.